Hi guys, I just thought maybe I can do some math lecture on the board today. Hi, Shirtless Guy here. Just felt like doing this. And rather than maybe do all new stuff, I think I might redo, just for another take of it, my three original thoughts in thought in math, which is Wiseman's theorem, Wiseman's formula, and Wiseman's identity. I've done it before, but maybe new people will see it again. Maybe a review, a new version of it, a new video of it will help more people to see it than if I just leave that one on and say, well, I did it and that's that. So I think I might review that today. And before I do that, I want to comment on the thing I said by Gauss. I think his whole name was Carl, I don't know. But when he did the one thing where you go 1 plus 2 plus 3 plus 4 and so forth up to 100, I explained how you take the opposites here, like 1 and 100 is 101, 2 and 99 is would be also 101, and so forth, and and the number of 101s you get is half the number of this, because it's two sets of these for two sets of two numbers it takes to get each 101. So that if it takes 2, then the number of 101s is this number divided by 2. But I didn't fully explain, just to make it clear, that the number you're multiplying that by is this number plus 1. So if I go 1 plus up to 100, it's 100 plus 1, which is 101, then times this number divided by 2. That should make sense, because it's this number plus 1 times this number divided by 2. And that's why that's the formula you get. You take this number, multiply it by this number plus 1, and divide all that by 2 to get the result. And like I said before, like we showed before, 101 plus 50, times 50, not plus, geez. 101 times 50, because 100 divided by 2 is 50, is 50/50. And that's the total of 1 to 100 all added together. So I didn't explain the little thing where you take this plus 1 times this divided by 2 and y. So I left that a little hanging last time, but this time I explained it, I think. So I'm going to go on with my own theorems and ideas. I'm going to say it again because, it's still original thought. Even if I say it every day, it's still important. It's still stuff I came up with. So Wiseman's, I'm going to write it up this time. Wiseman's, can I spell my name? Wiseman's theorem. THEOREM. It basically says that I took the number of dots it takes to make a square. That's not it, because that's 1 too many. And that's 9. It takes 9 dots to make a square, so I took that as my first number involved. And that took the number of dots that it takes to make a Star of David. So first, to make a Star of David, you make a triangle. That takes 4, 3, 2, and 1. Then to make a Star of David, you add 3 more, which makes 13. And it's like a Star of David there forms. And that is 13. I took those 2 as my first 2 numbers. So let's start with that. Get that out of the way first. And then I took those 2 numbers, 9 and 13. Let me put it down a little bit more. Let me put it down here. 9 and 13. I multiplied them by 3 and 4 in both cases. And what I found was 9 times 3 is 27. 3 times 13 is 39. 4 times 9 is 36. 4 times 13 is 52. And I noted that this is the number of books in the New Testament, this is the number of books in the Old Testament, and the total number of books in the Bible is 66, 2 6s. And I noticed that this is the number of black keys on the piano, this is the number of white keys on the piano, and this is the total number of total keys on a piano, 88. Not only that, this is double 6, this is double 8, and they're only 1 digit apart. There's 1 digit in between, which is 7. And this is Wiseman's theorem. I figured this out. I've never heard anyone even think about even coming close to even thinking about this question, much less figuring this out. So that's Wiseman's theorem. My first original thought in math. If you not counting those breakthroughs I was headed for at Harvey College before I left, of course. But that's above my pay grade now. I don't really remember all that math right now. Now Wiseman's. Yeah, I did the same mistake I did last time. Wiseman's formula. Now this, they teach us in school that the Pythagorean theorem. If you have 3 here, 4 here, and this is a right angle, this is 5, 3, 4, 5 triangle. Because in 2 dimensions, x squared plus y squared equals r squared, and 3 squared is 9, 4 squared is 16, and the total is 25, which is 5 squared. And that's cute, that's cool, 2 dimensions. And it also means that the area of a circle of radius 3 plus an area of a circle of radius 4 would be equal to the area of a circle of radius 5, because area is proportional to the square of the radius, because area is 2-dimensional and therefore you square it. R itself is only 1-dimensional, so it's just a number, and so is x and y. And this is cool, but I thought maybe it goes further. What if I tried it in 3 dimensions? What if I added another power to the equation and another variable? So what if I said, well, how about x cubed plus y cubed plus z cubed equals r cubed? That would be the three-dimension Pythagorean theorem to 3 dimensions. It would mean that if I go x this way, 3, y up this way, 4, and then 5 out of the page, which is 3-dimensional, from here to here would be 6. So 3 here, 3 here, 3 here, 4 here, 5 up would be 6 all the way to the start. And not only that, the volume of a sphere of radius, well, this is spherical. This is volume. This is not just area. But I thought, what is it that will it work for x equals 3, y equals 4, z equals 5, and r equals 6? Well, that just happened to work. Well, I figured it out. If I do 3 cubed plus 4 cubed plus 5 cubed, does that equal 6 cubed? Just a thought I had. I just thought, well, I might as well figure it out. Well, 3 cubed is 27. 4 cubed is 64. 5 cubed is 125, and the total is 216, which in fact is 6 cubed. So this actually works for x equals 3, y equals 4, z equals 5, and r equals now 6. Actually works. And I've never seen that. And then after I figured it out, I wanted to see how original it was, because I'd never seen it in any of my books I studied in school. No one ever told me about it, and I figured it out first. But I went to Sprague Library at Harvey College and went on the math floor and found a book from the Middle Ages. It's like 1300s or something, and it was a book written in the Dark Ages that actually had that formula, my formula, right there. But why did it get forgotten? Or if it wasn't forgotten, it was subverted. Why did it become subverted? Who subverted it and why? Is it because people don't like 666 being important in a formula? Because that's the devil? I don't know. Or did they just intentionally, or was it a mistake and they accidentally lost it in history? I don't know whether it was intentional or not. And if it was intentional, I don't know why. If it wasn't intentional, then it's just a mistake, and that's why. And that's Wiseman's formula. Now, my second original thought. It's almost a thought that's never been had, but that Dark Age math book proves me slightly wrong there. Oh, let's speak this up. I didn't mean to do that. Now I'm going to go Wiseman's. I did it right this time. I-T. Now, while I was playing around with numbers to powers, I thought, well, what about if I took higher powers other than 3? And I just figured out, it took me a whole day to do this, by the way. I just sat around the whole day good at this. And at the end of the day, all I figured out was that if you take 6 times 6 times 6 times 6 times 6, which incidentally is 5 sixes, as in 12, 6, 66 is my birthday. And this is 6 and 6, this is 6, 6, 6, and this is the times. So if you take the 5 sixes of my birthday, or just 5 sixes, whatever, and multiply them together, 6 times 6 times 6 times 6 times 6, that's 6 to the 5th power, of course. It'd be like, you could think of it as, besides my birthday way of looking at it, you could think of it as a pentagram. Oh, that's a great pentagram, Jimmy. Great. With 6 in each corner. That's another way of looking at it. 6 times 6 times 6 times 6 times 6. You can put a circle around it if you want to. You can put it upside down if you want to. You can do whatever you want if you want to, because you're free. It's America here. So what is 6 to the 5th power? It turns out it's equal to 7776. It's almost 777, but minus 1. So I thought, why not go 6 to the 5th power plus 1 equals 7777, which is interesting. Then why not divide this by 7 and this by 7, and I get Wiseman's identity, which is 6 to the 5th power, I'm not having much room here, plus 1 all over 7 equals 1, 1, 1, 1. That's Wiseman's identity. 6 to the 5th power plus 1 divided by 7 is 1,111. Interesting. I wonder if 1,111 is prime or not. I'd have to Google that. I'm not sure. If it isn't prime, if it's prime, that's that. But if it isn't prime, then what are its factors? I wonder. Anyway, I'll look that up later. Because 111 is not prime. It's 37 times 3. So what if 1,111 is also not prime? That'd be interesting. 6 to the power plus 1 over 7 equals, what's interesting about this too is that there's 4 ones, as in 4 fingers, a 1 over here, as in thumb, and 5 ones total. And not only that, thumbs and fingers are called digits, and so are numbers. There's that little coincidence. It has the numbers 5, 6, and 7 in a row, which are cool numbers, and they're not only that, there are 3 of them in a row. It's got addition, it's got multiplication, or at least division, which is the inverse of multiplication, so it's still multiplication. You could think of this as multiplying by 1 over 7. So it's still the multiplication operation, and it's got exponentiation, 6 to the 5th power. It's a beautiful little formula. I call it Wiseman's identity. So that's my 3 thoughts for math, or if you call this all math, or whatever you call it, philosophy, math, mathematical philosophy. Anyway, I love you guys. Peace, love, and rock and roll.